Now I'm going to continue with some topological properties of convex sets. Recall the following important concepts of sets in Rn. Now, let omega be a subset of Rn. A point omega in omega is called an interior point of omega if there exists r greater than 0 such that the ball with center at omega and radius r is a subset of omega. Okay, so here we have a set omega, and omega is called an interior point of omega if we can find r greater than 0 such that the ball with center at omega and radius r is a subset of omega. And the set of all interior points of omega is called the interior of omega, and is denoted by int of omega. I'm going to recall another important concept called the closure of a set omega. So the closure of omega is the intersection of all closed sets of Rn that contains omega. So the closure of omega is denoted by bar omega. It is the intersection of all set f such that f is closed and omega is a subset of f. Okay, so from this definition, we see that the closure of omega is the smallest closed set that contains omega. And then I'm going to recall another important property of the closure of omega. So we have the following important property. An element B belongs to the closure of omega if and only if for any r greater than 0 the ball with center at B and radius r intersects omega. So we can find these properties in most of the textbooks on real analysis. Okay. So next we're gonna talk about the closure and the interior of convex sets. We're gonna show that if a set omega is convex, then its interior and closure are convex sets as well. Okay. This is proposition 1.29 from the textbook. The interior int of omega and the closure bar omega of a convex set omega of Rn are convex. Okay. It seems that the proof that if omega is convex, then the closure of omega is convex. That part seems to be simpler, so I'm gonna prove first, and then I'm gonna show that the interior of omega is convex later. Okay, so the proof goes as follows. In the first part, I'm going to show that the closure of omega is convex. The idea of the proof is very simple. We're going to take any two elements of the closure of omega, and we're going to take any lambda in the interval 0, 1, and then we show that lambda a plus 1 minus lambda b belongs to the closure of omega as usual. Okay. So fix any a and b in the closure of omega. Then we find two sequences AK in omega and BK in omega such that AK converges to A and BK converges to B. Okay, so this property follows from this property. So we can easily show that an element B belongs to the closure of omega if and only if we can find a sequence in omega that converges to B. Okay, so if we have a set B and a set omega, and if we if B belongs to the closure of omega, then we can find a sequence Bn or Bk in omega that converges to this element B. Okay. at this point, we see that each AK and each BK belong to omega, and omega is convex. So we're going to take advantage of the convexity of omega to continue the proof. Okay, now we're going to fix any lambda in the interval 0, 1. Then lambda AK plus 1 minus lambda BK belongs to omega for all k in n. Okay? Again, this follows from the convexity of omega. AK and BK are in omega. Lambda is in the interval 0, 1. Therefore, lambda AK plus 1 minus lambda BK belongs to omega. Now, since lambda AK plus 1 minus lambda BK converges to lambda A plus 1 minus lambda B as k goes to infinity, we conclude that lambda A plus 1 minus lambda B belongs to the closure of omega. Okay, again, because we have found a sequence here. This sequence is in omega, and the sequence converges to lambda A plus 1 minus lambda B. Therefore, lambda A plus 1 minus lambda B belongs to the closure of omega by the property I mentioned earlier. Okay, so now I'm going to continue with the second part of the proof. In the second part, we're going to show that the interior of omega is convex. So to prove this property, we need to review some properties of open sets of Rn. So we can show the following property: if G is an open set of Rn, and A is an element of Rn, then this new set A plus G is open. Okay, again, this is a very familiar property for convex sets. For open sets in Rn, and we can also prove that if G is an open set of Rn and lambda is a non-zero scalar, then lambda lambda G is also open. Okay, and then we also use the following fact. Now, if G is if omega is any set, now if we can prove that for any omega in omega there exists an open set G that contains omega, and G is a subset of the set omega, then we can see that omega is also open. Okay, and so we can prove that easily because here G is open, so then you omega is in G, so you can find R greater than 0, so that the ball with center at omega and radius R is a subset of G, and then obviously it is also a subset of omega. Okay, so any point of omega is an interior point, and therefore omega is open. Okay, so now using these facts, we can show that the interior of omega is convex. Okay, so again we fix any A and B in omega. I'm sorry, in the interior of omega, and lambda in the interval 0, 1. Okay, then we find an open set V such that A belongs to V, and V is a subset of omega. Okay, again because A here is in the interior of omega, so we can choose R greater than 0 such that the open ball with center at A and radius R is a subset of omega. Okay, so here we can pick V, for instance, to be that open ball. Okay, be A R. Okay, then A belongs to V, and V is a subset of omega. Then we see the following: lambda A plus 1 minus lambda B belongs to lambda V plus 1 minus lambda times B. Okay, because V here is a subset of omega, B belongs to the interior of omega, so it is also in omega. We see that this new set here, is a subset of omega. Now, as mentioned before, this set here is open. Lambda V plus 1 minus lambda B, this set is an open set. How come this set is open? We see the following: lambda V plus 1 minus lambda B can be written as 1 minus lambda times lambda over 1 minus lambda V plus B. Because V is an open set, lambda over 1 minus lambda times V is also an open set. And then B plus this set is also open. And finally, because this new set is open, when we multiply by 1 minus lambda, which is a non-zero scalar, we have a new open set. Okay, so I can say since lambda V plus 1 minus lambda B is open, we see that lambda A plus 1 minus lambda B belongs to the interior of omega. Okay? Because there exists an open set of Rn that contains this point, and that open set is a subset of omega. Therefore, lambda A plus 1 minus lambda B belongs to the interior of omega. So we have shown that if we take any A and B in the interior of omega and we take any lambda in the interior of O01, then lambda A plus 1 minus lambda B belongs to the interior of omega. Therefore, the interior of omega is a convex set by the definition.